It's being live streamed. Okay, got it.
Right. So, if everything goes well, we'll be live now. Let's wait.
You know, I don't know.
Yes, excellent. Excellent. So we are live. Hello, guys.
Hello.
Thanks for waiting for us. This is the April event of Astronomy on Tap Vienna. Please write on the chat. Let us know that you're here as well. And with us, oh, hello, meeting music. Hello. Very nice to see you again. With us, we have Dr. Grigoris Maravelias from Greece. He's in Crete now, and he works at the National Observatory of Athens. Welcome, Grigoris. Very nice to have you with us today.
Thank you. Thanks for the invitation, first of all.
Yes, we are very excited to talk about your career, to talk about... Let us know that...
Sorry.
It's okay.
To open the chat also.
It happens to me too. Sometimes I have technical problems, so my viewers know that, but it's okay. It's okay. We're relaxed here. So today we will discuss about your career path, which is very interesting because it's a bit unconventional compared to the standard model, let's say. What you expect, a physics degree and then astrophysics, master's in astrophysics PhD. So it's a bit different, and we're very interested in that. And we will discuss about your research topics, which are massive. Very, very excited about that. We like to hear more and more about stars. And I hope our viewers like it also. We will also play a game together. And after the discussion with Grigoris, I will play the quiz with our viewers. So guys, I have put the link on the, I have put the link on the live chat. I will put it again. This is the quiz link. So you can already start playing if you want. And hello. Hello, Antonis. Hello, Nadia. Okay. Hey, guys. Great to see you. Thank you very much for joining. This is amazing. Good. So, Grigoris, tell us a bit what inspired you to get into the astrophysics world, right?
Get into astrophysics. Interesting question. I think in most cases, some of us, they are born with this gene mutation or disease. I don't know how to call it exactly. That you have an urge to look. To study or investigate these kind of things. Naturally, humans are attracted by the night sky because of all the questions regarding the human existence and our places in the world. This is, it may sound, it is philosophical, but it is something which is, I think, valid across the time. But apart from this, it's something that comes somehow naturally. As far as I remember, I really enjoyed, reading or watching things about the universe and having discussions on the summer starry nights, especially here in Greece, actually. So let's say that the motivation was there, but of course, as you grow up as a kid, things change, you have other priorities, you think in a different way. So yeah, but sometimes this persists throughout your life, and you cannot do anything else than just accept it, embrace it, go on with it, something like that.
You speak of it like it's, you cannot get rid of it. Like
I can't. That's I don't know, that's a fortunate and unfortunate thing at the same time.
Okay, it's a brain parasite or something. Well, it's good because it brought you to this magnificent world from, as I said before, an unconventional path, but you didn't study physics.
I studied physics, but it's not, let's say that the direct path is, to go to a physics department, do a master on astronomy, a PhD in astrophysics or astronomy, then and start working directly. So my path is not direct in that sense, because I went to the National Technical University of Athens, which is considered an engineering school. So after a 5 years bachelor, I went on to do a master in microelectronics and optoelectronics, actually, at the University of Crete. Then, so far we have 7 years, right? Then I went to serve my obligatory military service for about a year. Then I returned to Crete to work as a lab technician, laser engineer at my previous lab, which was, by the way, it was really a good experience with great people. I'm really happy with this collaboration. I had a very good time, but it was just myself not very inspired or motivated for this job. It's not that the subject is interesting, but probably for other people, not me. It is just, so it's, I mean, it's a natural thing to have a personal preferences, right? Yeah. So in that sense, I was always motivated and I was always passionate about astronomy. I was an amateur astronomer since end of 90s, 2000, with observations of variable stars, of meteors, by eye or by using telescope, binoculars, things like that. So I found myself always trying to find time to work on these things more and more. So at the end, I said, okay, I'm going to resign from my job and start to, go after this dream, actually. I was lucky enough to get a scholarship. So then in 2010, I started my PhD at the University of Crete, which I fulfilled in 2014. And since then, I went as a postdoc initially in Czech Republic for 2.5 years. Then another 9 months in Chile, and then back in Greece, where I work since then.
Mm-hmm. So you traveled also because of that. So you did this classic postdoc, going from country to country path.
It is inevitable, actually. I mean, there are good things, of course, in this, in the sense that we're getting a lot of experience, international collaboration. It is really challenging for your personality, both as a person, how you live in a foreign country, and as a scientist. But then, it is always, it was for personal reasons that I returned to Crete, of course.
Do you like my floating head? I have a floating head here.
Yeah. So, yes. And I would like, to some extent, I would like to stress that, of course, there are direct paths, and there are also other kind of paths that can lead to astronomy. And nowadays, it is even more important because, for example, computer scientists can be very much active in our science or community dealing with computational subjects.
Yes, it's very important because we know now, we have already talked also in this series of podcasts about machine learning and how we use it to analyze our data. So also, not only that, to understand our telescopes and analyze the data from the telescopes and improve the performance of the telescopes.
Sure, the engineering approach, especially for the modern instruments, is very, very challenging, and you need to be very, very well trained in order to build instruments. Or you
need to be a specialist. You cannot be an astronomer doing cosmology, for example, and at the same time build the software for a telescope, because it's very, very specialized, or the hardware for the telescope. It's something very, very specialized. Yeah.
This is actually what I took advantage from my career, because as I said, I went to the National Technical University of Athens, which is an engineering school, but the courses were, I studied applied physics and mathematics, which means that I had a strong background in mathematics, physics, and computing. So all these skills add to the final product, let's say. All of these contribute for the development or for the personal development, so you can use them actually in any case.
That's very nice. And so you decided to go into astronomy, and what did you what was your topic? What did you choose, and what are you studying?
Yes, so through my PhD, I studied mostly. I was involved with the optical observations of high mass X-ray binaries. So these are actually binary systems in which you have one compact object, as we say, which is either a neutron star or a black hole, which accretes, which means that attracts material from the other part of from the companion, as we say, which can be a massive star. Mm-hmm. So what is going on in this case is that you have the accretion, well, that's the technical term. I mean, you have the flow of material that goes around the compact object, because the compact object of
like here?
Yeah, exactly. That's the background of image. So you see on the right side of LNE, you see the donor star, which have generally have these stars have strong stellar winds, so they release matter. And because of the strong gravitational pull of the companion, which in this case is a black hole, this is attracted, and actually it goes into orbit around the black hole, and at the end, it accelerates, and this releases X-ray emission. So you see these as bright sources when you observe them with X-ray telescopes like XMM Newton, Chandra.
Space telescopes. Yes.
Yeah, space telescopes. Yeah. You cannot see X-rays from the ground. Yes. What you can see from the ground is the optical companion of this, because the donor, for example, it's a normal type star, so they emit most of the light in the optical, actually in the UV, but anyhow, an important fraction is emitted in the optical, so you can see it also through ground-based telescope.
Good. I want to learn more about these massive stars
like
that you're studying. A lot. I want to learn everything, right? And I want our viewers to learn everything about them.
So first of all, we start by the fact that we don't know everything. So that should be enough, right?
Yes, that's a good start.
Yeah. So yeah, I mean, I will need some help here in order to drive me. I mean, massive stars are, what we consider as massive stars. Yes. Are the ones that are above 8 times the mass of our sun.
Yes.
So, and they can be up to really, really a lot, like
50.
50, no.
Okay.
Try another guess. Let's see.
15.
15.
Yes.
15.
More. Okay, 25.
25. No. We're talking about up to 300 solar masses.
Oh, more! Oh my God! Okay.
So, I mean, that's also, let's say, caveat in the sense that we are not exactly certain what's the upper limit. I mean, theoretically, of course, this is a matter of debate. I mean, theoretically, we were expecting stars up to 100 or 150 solar masses, because after this, the radiation of the star is so strong that it can dissolve the star. But in practice, what we know is that things can be a bit higher than this, I mean, in reality. So again, what we know for certain is that we have measured very robustly masses of up to 150 solar masses. Solar masses. And these are from observations of eclipsing binaries, from which we can determine the mass ratio of the two components and the inclination of the system. So we can solve accurately and define the masses. Now, for the ones that I talked before, like in the 315 solar masses, this is the estimate of one source in the Large Magellanic Cloud, in a cluster in the Large Magellanic Cloud. This is obtained by using models. So it depends actually on the details of the models and how accurate you are. I mean, you are constrained by the models in this case.
So you observe stars in our galaxy, but also in nearby galaxies, right?
Yes, yes. Massive stars are the ones that are mostly more luminous, so you can see them even in galaxies further away, like
Okay.
megaparsec away in the local universe.
Yes. I'm not sure that our viewers are familiar with the megaparsec, but
Yeah.
a
So,
few million light years, or
what is it? Megaparsec is.
fast math. I don't remember.
Yeah.
But it's not. But it's not what they say on Star Wars. It's not.
Yeah, it's about 4 light years, something
3
like
light
that.
years,
So,
something light years. Yeah. Okay.
about 4 times the value, like 20 mega light years, something like that.
So a few million light years.
Yes.
And the light year is the time that light takes to go from one place to the other, basically.
The distance that the light travels within.
Yeah, the distance the light travels. Yes, thank you very much. Yes, so you study these massive stars in our galaxy and far away, and you can see them because they're big, right? But are they very is it very frequent to find them, or are they rare, and why?
In reality, massive stars are very, very rare. I mean, I like to use a quote by Phil Massey that he said in one paper that you have about 1 star of 10 solar masses for every 100,000 stars of solar type. And you have about 1 star of 100 solar mass for every million suns. Okay. So these are very rare. But it's very, very interesting objects because exactly they are very rare, but on the other hand, they play a very critical role in many, many instances.
That is very interesting.
Yeah.
Do tell us.
First of all, there are great engines to produce elements. I mean, because of the huge masses. So one basic thing is that a star's life is always a balance between how the gravity presses the material and how the material reacts to this pressure. I mean, you have gas, which is in an ionized state, and this produces radiation. So the radiation tends to push the material up, if we think 1D, and the gravity tends to push the material down. So the balance between these two characterize the life of a star. If you have instances where the radiation is more important, then you have, let's say, an extension of the atmosphere of the layers. If the gravity is more intense, then this push the material, it suppresses, it presses more, it increases the temperature, so you have production of other elements that, as they go on, they produce another kind of radiation, they produce other radiation, and then you regain the balance. So it's always a fight between these two forces. Of course, it's more complicated than this, because other parameters can play a role, like the rotation of the stars, the metallicity. But as a summary, this is the main, let's say, driving mechanism.
So they create elements that the other stars don't create.
Yes. So the point is that through this process, they are producing more and more heavy elements as they try to burn. I mean, at the beginning, they burn the hydrogen. After this, there are some leftovers like helium. Then they start burning helium, and then they go on to burn elements like oxygen, neon, and stuff up to iron. They cannot burn further iron, so this is the end point for most of them. I mean, if we are talking about massive stars, this is the end point from which after that, they actually die. But the point is that they are producing a lot of elements, and and these are the same elements that we have in Earth. I mean, all carbon from which we consist of has been formed in the stars. So this is also another famous quote by Carl Sagan, who says that we are stardust, right? I mean, it's very, very accurate. So this is one critical aspect. Then the other thing is that they interact a lot with the interstellar medium. What I mean is that these stars have strong stellar winds. The wind is what people have heard already about the solar wind. The particles that leave sun and they hit the atmosphere and they produce all the auroras.
The aurora, yes.
So it is the same thing, but it is much more intense because you have a lot of mass. So this actually puts a lot of energy and momentum and actually shapes the matter. I mean, if you have matter lying around in the region of a massive star, this is affected by the momentum and these winds. So in that sense, they're actually shaping the one. You can see various shells or disks around these stars, and also which is connected with the nucleosynthesis that I said before. All this matter, all these elements that are produced in the cores, at some point they leave the star and they go into the interstellar medium and the intergalactic medium. So in that sense, they provide enrichment of the immediate environment and as a result of the host galaxy. So they enrich the whole galaxy with more metals, as we say.
Okay. And then new stars can be born from these materials, right?
Exactly. Yeah. Also, because of this, for example, when you have a strong stellar winds, this can suppress matter which is further away, and then this can contract to create other stars. So they can trigger star formation.
Oh, okay.
What else?
Interesting. And you said that they are very hot, right? Sorry, I just I stayed to a thing that you said that these massive stars are very hot. Are there much?
I would like to add the 2 points important for this, because there are also another 2 things that are important. And first of all is that apart from this, they are also the progenitors of the most compact objects that we know, like black holes and neutron stars.
Okay.
And they are the progenitors of some of the most energetic phenomena in the universe, like gamma ray bursts and even gravitational waves.
Oh, okay.
These remnants, like black holes or neutron stars, from these massive stars can actually merge and produce the gravitational waves. And at the end, something also to point is that these are the stars that we can study right now in order to understand and possibly speculate actually what was going on at the very, very early beginning of the universe. Because at the very early beginning, you had massive stars, very massive stars as they go. So they were about hundreds or thousands of solar masses. So in order to understand this, I mean, this hypothesis, we haven't observed any of this. I mean, there is some hope now with James Webb Space Telescope, but nevertheless, it's a theoretical aspect for now. But in order to understand it, we need to understand the massive stars, the most massive stars that we have now.
Okay. Grigori, is this because there was more dust in the beginning, or why?
On the contrary, we didn't have so much dust. We had a lot of ionized gas.
You had a lot of ionized gas.
Hydrogen and high energy, so we had the formation. Now, we don't know exactly how these are formed. I mean, of course, you have the concentration of gas and the contraction and all this, but it is really a question of how these were formed, especially very fast in the beginning, because even at the very, very early beginning, we see galaxies and clusters, and this is not easily answered from the current models. How fast you can create this.
Yeah, we still don't have an answer of that. Of course, every field in astrophysics has high hopes for James Webb to understand what happens in the early universe, right?
Yes, I think
But these stars were different. The massive stars at the beginning of the universe were different from the massive stars now, different generation, right? So they had different materials that they were made of.
Actually, they were made only by hydrogen because there were no, hydrogen, a bit of helium, and tiny lithium at the beginning of the universe. So you didn't have any other kind of elements. So after these stars were born, they produced some of these elements and they contribute to the enrichment that we observe nowadays.
Yeah.
And that makes a difference because stellar winds are, for example, more intense when you have more metals than.
Okay. So now the phenomena of enriching, as you said, the interstellar medium, so their environment is more intense than it was in the past. Okay. And I wanted to just point out, I'm sure our viewers already know this because they have been, we have been explaining stellar evolution for some time now, but what you said about the black hole, so a massive star will eventually end up being a black hole because it releases all the cells that it has, right? So it will explode at some point or implode into a
well, yeah, it is a bit more complicated because when we want to discuss about that, then you need to take into consideration a lot of parameters like mass loss, which is exactly the stellar winds. You take into account the rotation, how fast the rotation is, that because this affects the internal mixing of the elements. Or you have to take into account metallicity, what is the fraction of the metals. If you have a high fraction of metals, then your stellar winds are more intense. What does this mean? It means that the star loses more mass during its life. So at the end, you will have a lower final product, a lower mass product. So that determines if this will become a neutron star or a black hole.
I see. Okay.
And you have a different also ways to die, in the sense you don't have 1 million ways to die. You have less, but still they are different depending on the various conditions, let's say.
Okay.
When you can have a core collapse supernova, which means that everything after the loss of support because of the internal radiation, then everything collapses, and this may increases the temperature extremely in the core, and then this pushes back and explodes, and you release all the material. But then you may have other kinds of exotic, let's say, things like instability or electron capsule supernova, which can
those are very fancy things.
I mean,
it
it's more technical then, but the point is that they are not, people try to do that with stellar evolution models to derive the parameters and define regions in which you get a black hole or a neutron star. But as you understand, we know a lot of stuff, but we are still missing quite a few in order to make accurate predictions. Things are improving a lot, especially in the last decade or so. There have been many model codes with respect to that, and people are working a lot on this. And we see a lot of improvement on these predictions.
Okay, good.
But there are still things like convergence of the code. For example, I don't remember the exact value, but a star of 20 solar masses could explode as a black hole, but 21 wouldn't explode. So you try to understand why this can be just a code, just a convergence of the code.
So as you say, it's not so linear, it's a more complicated issue. So a lot of parameters account for the path, final path. But compared to the sun, let's say, how long does a massive star live? I mean, what's the lifetime?
Well, compared to the sun, all massive stars will have died already.
Okay. Okay, so the sun is 4.5 billion years old.
Yes, I mean, the most massive stars, like early O-type stars, would live for a few mega years, 2-3 mega years, million.
So a few million years, okay.
Yeah, because the actually analog for this is that as more massive a star is, then it consumes more with a greater rate. It's it's fuel.
Is it also hotter than the sun?
Definitely, yeah,
Okay.
definitely. These stars, I mean, when they're in the main sequence, there are some talking about massive stars of B type, let's say, this can be from 25,000 Kelvin up to 150,000 Kelvin. Extremely hot.
Extreme. And how much is the sun?
About
a few thousand?
5,000, yes.
Okay. Wow, okay. Getting hot.
Sorry, this is the effective temperature, which means the one that is close to the surface, not the one at the core, which is about 1 million also.
Okay.
Or the corona, which is also about 1 million, if I remember correctly.
Mm-hmm.
Sorry, from the solar guys, I'm not very well informed about this.
we can get a solar guy next time to explain more things to us. Okay, so I have another question. How far is the furthest massive star that you have observed up to now? It's not the beginning of the universe because you don't have James Webb data yet.
Yes. Is the question personal in the sense what I have observed or what we have observed?
Sure. Why don't you tell us a bit of what your accomplishments? We want to promote.
I don't remember that.
So
but there are a few.
My data is the best.
But there are a few close to mega years again. I mean,
so a few million light years.
Yes,
okay.
yes.
Yeah.
Now the furthest one, I think there is a claim lately, or like a few days, weeks, that they said that they they observed a massive star, as they comment, around about 1 million years after the birth of the universe at Z redshift 6.2, if I remember correctly. Okay. So this, of course, is not a direct observation. It is an event that is obtained through the gravitational lensing effect. So what that means so I suppose that most people know that the space is curved because of the gravity. So in that sense, if you have a very massive source, you can see, because of the curvature, you may see something behind this, if all geometry is correct in order to see these effects. And then they notice actually a point in the pictures that didn't change its position, I think, for some years, and it is unresolved, which means that it's it is not lensed by more than, it's not lensed more, I think. I don't know exactly the details. So their assumption is that this is a stellar source, and above 50 solar masses, perhaps 150 solar masses, but this remains to be resolved more, because you may claim that this is a star, but what happens with massive stars is the following, that because of the problem, let's say, that the massive stars is that they are not singles. In most cases, they are binaries or triple systems. Okay. So what you see, it can be more than one star in many cases.
I see.
So this is a common problem which we have faced especially in nearby galaxies, because you see a point at the beginning, you say, that's a point source. Okay, great, it's a star. Then you put it in the model and it may fit or may not fit the models. And then you use HST imaging, and then you see that that's a cluster.
Okay, good. The Hubble Space Telescope that has better resolution, right?
Yeah, for sure. So it remains to be seen if this is, a single star or this is a cluster of stars. So.
Okay. You said something very interesting that I will keep in my mind about double and triple systems, and I want to discuss this, and I want you to tell us also about X-ray binaries that you already hinted a bit before. But now, let's play a game. Let's take a breather from massive stars, because I think I asked all my questions. Guys from home, if you have questions, tell us. Sorry, I was not looking at the chat until now. You have told us, yes, thank you very much for telling us how much a parsec is. And good evening to you too, Labro. Good. We will play a game with Grigoris. I will let him have a drink. I will also have a drink. Cheers. Okay.
I just have water this time.
Maybe you can see it, maybe not. This filter is... it
filters out, right?
Sucked.
Because
it's getting sucked in. Oh no, it's getting sucked in. Okay, so we will play a game, Grigori. It's nothing. It's nothing. It's called true or false. It's very easy. I found the most difficult questions online, and you will answer them.
Good. Let's get embarrassed publicly.
It's okay. I do this every month. I embarrass myself at least once live. So
yeah, it's nice to humiliate yourself.
Yes. Good. Right. So for true, you go up. For false, you go down, or you can say true or false. So the first one. Okay, we're starting. Are stars hydrogen bombs?
Hydrogen bombs? No. Okay.
I think it's a popular question, right? You know, these frequently asked questions. I mean, yes, you have nucleosynthesis, you're burning hydrogen to helium, but it's not a bomb. We cannot say that.
Else you wouldn't have them. Because it's a reaction that, let's say, it is remaining under control.
Yes, it's under control for now. For the next 4.5 billion years. Until the sun eats all of us. Okay, the second one. Massive stars are blue.
No, definitely not. It depends on the... It depends on the evolutionary path. I mean, you may have most of them blue in the sense that they are the hottest part, but you actually have yellow hypergiants or red supergiants, which of course are huge stars. Like, I mean, in the sense that, and these are cooler in the sense that they are about 5,000 Kelvin or less for red supergiants.
Okay, so I'm so happy to have an expert here, because if you go online and you Google this, for example, it will tell you yes. And that's the most, this is what I also remember from my university years when we did Introduction to Astronomy, for example, right?
Well, I mean, it comes to the details. If you're talking about main sequence stars, so what that means, the ones that burn hydrogen in the core, then yes, these are blue. But if you talk about the Vol stars, which travel and they go to the cool part, then no, you can have supergiants which are massive and be on the cooler side. And there are actually these kind of examples. For example, Betelgeuse, a very famous one. It's about 14, 15 solar mass. Right, so it's a massive star and it's red.
Yeah. Okay. Good. Right. The third one. The most massive known star is R136A1,
yes.
And it is 100 times the mass of our sun.
100? No, we said it's about 315.
Okay, good. Yes.
That's the one in one of, I mean, R136. It's a cluster in LMC, in the Large Magellan Cloud. And I mean, it was considered point source. Then they resolved that to a cluster. And then they found these sources called A1, A, B, C, D. And then they noticed that A, it's not one star, it's more. So that A1, A2.
That's why it has the A1 here.
Exactly.
Okay. Nice. Okay. 4. A star like the sun can burn hydrogen for about 10 billion years.
Yes.
Okay. It's very easy.
Come on,
give me more difficult questions. You want more difficult, I know. Okay. So
I was expecting, what is the clamping ratio in Wufraget stars?
Here, so listen, here we take it back to the basis.
Sure. I'm just kidding.
So here we keep it relaxed, we keep it casual, and we always have drinks. So things are very relaxed. Sometimes the questions are difficult, but sometimes are very easy. And because you are an expert, they are very easy for you. So I didn't do the fifth one. Okay, 5. A massive star can burn hydrogen for 100 million years.
A massive star can for 100 million.
100 million.
If you consider massive stars or big stars, no, I think it's too long.
Okay. No. Yes. Good. I think this is good. Yes. False. I found a few million years. Is this correct?
This is correct for the most massive, but you can still have massive stars, which can be up to 40, 50 mega years. Okay. Perhaps it can go up to 100. So, I mean, this depends also on the metallicity now.
Good. Next one. You're doing very well. So, 6. There are 200 billion trillion stars in the universe. Wow.
I don't know if this is more than the sand grains in Earth. Then yes. If no, no.
Yeah. Excellent. Yes. So that answers the other questions. Are there more stars in the universe, or dust grains in sand grains in the Earth? Good. Yes, I also found this true. But I haven't done the calculations myself. If the star is massive enough, it can collapse directly to form a black hole without a supernova explosion in less than half a second.
I don't know about the time scale, but it seems reasonable. I mean, even the supernova explosions are, the final stage it can be a few seconds, something like that. That's why you have a lot of you can have GRB or these gamma ray bursts of X-ray emission because you get unbelievable conditions.
Okay, interesting. Okay, the last one. All X-ray binaries contain a black hole.
No.
Okay.
No.
But,
because you may have actually neutron stars.
Okay, so sorry, my kid is doing acrobatics. I have the link. So excellent, because this brings me back to my question about X-ray binaries. You said something before. I want to ask, why are they so important why do we want to study them? And also the other thing that you mentioned, you cannot see it. It's very nice. I'm being abused. I think he's bored. Playing too much Fortnite today. Okay, πήγαινε μέσα. That was a small break for advertisements.
That's a small peak. That's a peak of daily life.
Yeah, that's a peak of daily life for the ones with parents. Oh my God!
It's just that I have managed to arrange that. That's why you don't see any background noise. You don't see any intruders. It's because that.
Usually he just plays Fortnite and everything is very quiet. But today it's holiday here and. Πρόσεχε, κοίτα, θα πέσουν αυτά και θα γίνει ζημιά. So it's holiday here, and I think he reached his limit with Fortnite. I mean, how much can you play?
Imagine getting saturated by playing a video game.
Yeah. So, Grigori, I'm interested about the X-ray binaries, and I want to understand why it's important to study them. And also the other thing that you said, that we're trying to find one star, right? One massive star, and we end up finding 2 or 3, so they come in groups. So that was also very interesting.
Okay, let me answer the first part, and then I will ask you again to repeat the question for a second. So, why X-ray binaries are interesting? First of all, because you have a laboratory to study extreme conditions of temperature and gravity that you cannot really achieve in Earth. I mean, right? It's millions of degrees of temperature close to the compact objects. You have extreme gravity, you have black holes in neutron star. So these probe extreme, let's say, physics. So you test a lot of knowledge with respect to this. Then the other interesting thing is that they provide important clues with respect to stellar evolution. As we said before, we have. I mean, one thing is that we have a lot of stellar evolutionary models. These models try to take into account all physics that we know with respect to the internal structure of the star, how this changes with time, how this is affected by the mass loss, rotation, metallicity, whatever. And then you have also binaries. So you have another companion that when you put next to the source that you have, this changes the evolution of the star. So you may have mass transfer. You have mass transfer, and this changes a lot what the end product will be. So X-ray binaries provide clues about this because they are unique objects in the sense that in order to produce the black hole or the neutron star, you need to have the supernova explosion. Okay. But in most cases, if you have two stars and one of them go boom, then the binary in most cases will dissolve. So the other one will receive, most probably the compact object, if it's single star, will receive a kick and it will go away. But if the conditions are the ideal one, then you may still get a bound system. So that's an important thing when you try to do simulations. You need to understand how you can reproduce what we see. I mean, we take into account the population of X-ray binaries that we have, of the population of stars initially, and if you put all these things into a blender, you try to understand if what you get from this resembles what you see in nature. So this can give you ideas of what are the channels that produce these sources, and again gives you critical ideas about what is going on. Then the other thing is the evolution of this. You have a compact binary, right? Compact object, and then you have another star. At some point, this star will also explode. So it will eventually give you either a neutron star or a black hole. Then you end up with neutron star or neutron and a black hole. And these are the prime candidates of gravitational waves, which is something that actually matured, let's say, the last 10 years with the detection of the first gravitational waves. So we enter this multi-messenger era where you can combine information across the electromagnetic and the gravitational
and
the spectrum and the gravitational waves.
Okay, and with your work, you do the observational part, right? So you provide all the observations that the theoretician will need to make the simulations.
Okay, it's not that. Let's say that.
Not all the observations.
That broaden, let's say. But the point is that what I have been doing is one part of my work was during my PhD was to do the optical classification. So that means to observe the donors, the stars, from ground-based observations and understand what are the properties of these objects and try to confirm that these are, let's say, the X-ray binaries. This gives you a census of these systems, and then you can start playing with the populations and try to understand if this, for example, changes, if this properties changes with metallicity, and what this can tell you about these systems. So yeah, I mean, that was one of the basic work, and there's some, let's say, the optical properties of these systems.
And now, what do you focus on?
Now I have, through my postdoc, I have started working on more, not more massive, on massive stars, but on the mostly on the optical part and different, let's say, flavors of massive stars, like in particular B bracket T supergiants, let's say. So this more technical again, more detailed. So lately I try to work with, let's say, all kinds of massive stars, all the zoo that we have. And then over the last few years, I've been also involved with machine learning applications to solve astrophysical problems. So, for example, now that I work for the National Observatory of Athens, I'm working for Alkisti Bonanos in an ERC project that has with respect to estimate the importance of episodic mass loss in massive stars. This is a huge project, of course, with many people involved and many parallel, let's say, sub-projects that are underway in order to understand how this, how the mass loss and especially the outbursts of all these supergiants change with respect to metallicity and what this means for these sources. And then for this, I was responsible to develop a machine learning classifier using photometry across different bands in order to try to, using these bands, to classify the sources as, you know, red supergiant, blue supergiant, or something else.
So you're putting little tags on them and name them.
Actually put the labels, because in order to have a secure classification, you need the spectrum. But in order to get spectra for these sources in nearby galaxies, you need 8 to 10 meter telescopes. So you need the cutting edge instrumentation to perform that. And also, as you very well, you know very well, time at these facilities is not given easily. So you need to submit a proposal, and the proposal should be very solid to get the time. We were very happy to get some like 80 to 100 hours of observing time in these facilities. So it's quite a lot of time. And for this, we're getting spectra for some of these sources. And in order to maximize the efficiency, we need to put some knowledge behind the selection of these sources. And so this has been what I have been working the last few years, and now we have the first paper about the method published, and we are working on the full catalogs now to produce these predictions and start working on the results, which are how these predictions behave, let's say, with metallicity. That's the major aspect for my work, of course. I mean, on parallel, we do have this spectra taken, which will confirm the credibility of the classifier, or they will actually help it improve.
Okay, that sounds very exciting, and congratulations on the publication.
Yeah, thanks.
I know it's not easy, and our viewers should know it takes a lot of effort to reach to that point. So your research sounds fantastic, and I wish you the best for the continuation. I will go back to my 3-body question.
Okay, yes.
And then we will take it a bit outside research to tell us your activities outside. So, yes, my question before was if it's very common to find these massive stars in 2 or 3 3-body systems.
Yeah. Very common. I mean, for the most massive stars, when they were born typically in binaries or triples or multiples. I mean, you have a concentration of stars born, let's say, all together by time. So it is actually, I mean, the latest works have shown that the binary fraction is very, very large on this, like more than 80%, for example. And this actually drops a bit as you go to, let's say, cooler or less massive stars, but for massive stars, it's very, very critical.
Good. Right. I think that wraps the research part, and I have a question. I know you do a lot of things outside, astrophysics research, and you've been involved for many, many years now, like of the order of 20, with outreach activities and observing. And tell us a bit about it.
Yes. So in many cases, perhaps I should consider myself an amateur astronomer that became professional, because, as I said at the beginning, I started doing things for astronomy around the end of 90s or beginning of 2000 with respect to observation, like trying to observe variable stars using the eye or binoculars and things like that. Meteors, for example, which may be silly, but it's very, very funny to do. And it's actually very valuable with respect to the flux of incoming material. So to that extent, we tried really hard from the beginning to actually popularize the observational part of astronomy. I mean, yeah, of course, outreach is everything that has to do with, let's say, promoting astronomy, like going outside with the public or in a school and observing the planets and stuff. But and I have, of course, taken part in this kind of activities, but I actually focused mostly on how you can train people of any age, of course, into producing scientific useful results. This means, for example, how you can do an estimate of a variable star in order to put this point and send it, of course, to some kind of databases and stuff, and let astronomers later on use these estimates. And actually, I do have a recent publication also that came that was in the press now, has to do with Rho Cassiopeia, which is a yellow hypergiant. I think it's the brightest one. You can see that in the Cassiopeia. It's about 4 magnitude, so you can see that by naked eye. And for this, you can really do easily estimates of its visual brightness. And I have performed an analysis in order to analyze the outburst of Rho Cassiopeia, which has been for the last 120 years. And this proves how useful this is, actually. I mean, using only the visual estimates, we can see the trend of the outburst in this star and what is perhaps predict some future behavior on this, which is very important. Another thing, and this is also another project that came out recently, is helping actually contributing with some kind of statistical approaches. A friend regarding observations of Venus. So in this work, what Manos Kardas, the person that did all the work, is he used his telescope in order to obtain observations of Venus, and he took into consideration other images that he found online in various international databases in order to monitor a recently newly discovered phenomenon, which is global scale wave in the atmosphere of Venus. And actually, this shows how important is the contribution of amateur astronomers even now, even in the era of large facilities and even larger, like the 30-meter telescopes that are built right now. I think it's a misconception that because of the large telescopes, amateurs do not have place. Because the reality is that these facilities, which are going to be huge, and of course they have the advantage of latest, of largest mirrors, of latest instrument. They can do a lot, but all the community will ask time for this. So they don't have the time to give you, for example, in order to investigate one particular star and what it does. Also, if you're interested in long-term behavior, then you need dedicated monitoring of this kind of stuff. These facilities cannot provide this. They cannot give you, one night per month to do this. It's impossible, right? So there is still a lot of room for people with telescope or other renting or using other equipment. Of course, also through citizen science, which is very, very popular nowadays, they can actually contribute to science. And this has been a main focus of my attempts in order to popularize and train people towards this direction, more than, doing outreach activities like performing public talks and things like that.
Yeah, so that's very important that you say that. And I totally agree that it's impossible to do all the science that actually needs to be done to understand the universe with big facilities. It's going to be impossible to get time, even to do very trendy projects. We are all competing for one thing. It's not going to happen. And we don't have the time. Also, sometimes professional astronomers, because they work in these big collaborative groups, they don't have the time to do, as you say, maybe some monitoring or some object by object observations. They go for statistical observations now. Machine learning is very popular. So I think it's a very good idea to keep people that are interested in the loop and teaching them the skills to perform this analysis and contribute.
Actually, this is also a nice point that, apart from doing your own observation, which of course a great experience, to have your own equipment and doing things like that. Also the learning curve is very, very steep on this. But apart from this, something which is very interesting nowadays is that you have access also to databases. So you can actually, with the help of, with the help of some people that know how to handle this kind of a database, you can actually study or discover things even without using a telescope, just sitting at the computer. The Galaxy Zoo is a great example of this. Yeah. And due to the incoming of these large facilities with huge data income, there's going to be a need to actually there's going to be a need in exploiting this data. And actually, it is interesting because there are also, as you know, there's also funding to do archive work. So you submit a proposal to get some money. I don't know if money are always part of this, but in order to have access at least and work on the archives, because there are many data that are sitting and nobody has looked them thoroughly. So it is an era that both, let's say, equipment or telescope time will be needed for follow-up observations, especially, and with respect to data analysis, for sure.
Yeah. Definitely. So a lot of possibilities there for everyone, and I hope our viewers get something from this, and if they like astronomy, they can get involved in many ways. You don't have to be a professional astronomer. You can contribute in other ways through citizen science, for example. So you can go to the Zooniverse project and find some projects there to classify objects, for example. There are many different kinds of projects. There's a gravity project, there is a Radio Galaxy Zoo project.
Yeah, and there are continuously new projects added, or there are new ideas, or there are also other projects, perhaps more detailed, which are not on the Galaxy Zoo, for example.
Yeah. Very nice. Okay, Grigori, I have you here for a long time. I have one last question because I asked everyone this question and I want also to hear what you think. What do you think, in your opinion, is going to be the next big discovery?
Hands down, aliens. That definitely will be the next big surprise, right?
Yeah, you know, after these last 2 years, we're not surprised by anything anymore. So yeah, why not? Sure.
In Greece, at least, yes. We don't know.
Like,
they may already exist, you know.
It's like, oh, there's a ship above Vienna. Oh, okay.
Okay, yeah. Joke aside, I think that the most important results will come out from James Webb Space Telescope now, because I mean, first of all, it is finally launched. Let's take this as a huge step. Now, of course, the next thing is to see that everything will go perfectly well when deploying. And I think then we'll see very, very exciting things, because it's going to be a very large instrument looking through infrared. So we are going to look inside areas that will not, it was not possible before.
Back in time.
Yes, and I think that will be the most important, especially for the early universe, which is very important to understand questions there. Of course, there are many other points like galaxy evolution that you are aware of most. I don't know so much about that. Exoplanets, okay, possibly.
Yeah.
I don't know, but yeah, it's
one of the big topics. Yeah.
Sure, but yeah, I mean, to me, it's mostly that we are going to, I think we are going to succeed in identifying, let's say, elements or molecules in other atmospheres, but I think we will not be able to do much after that. And I think this is not going to be done also with so much with JWST, but we have also other dedicated exoplanet missions on this. So I think that will be the most, let's say, secure bet, in the sense that this will actually show us hopefully things that we haven't seen before. Now, yeah, I think that would be my guess, let's say.
You're a bit biased towards the infrared. It's okay. I'm a bit biased towards the radio. So I would say the square kilometer array, for example, that will solve.
I agree.
Listen. It will tell us everything about radio sources in the whole universe and about magnetism that we don't know shit, basically. So, my friend.
Magnetism is the, you know, the, how can we say that? It's a jack, you know, whenever you need something to put some meaning when you don't know what to do, is either binaries for stellar astrophysics. You put binaries and that's over, then you have problem solved, or magnetism.
Magnetism for galaxies and clusters and things. Yes, definitely. Or if you don't have a question, you know, in conferences, if you don't have a question or in meetings, you always ask about what about the magnetic field.
Yeah, I mean, for stellar communities, it's like, well, what if it is a binary?
Very good. Very good. Excellent. Okay, great. Okay, this conversation has been amazing. I want to keep you more, but I know we have exceeded our time, and I don't want to, as we said, we have busy days.
Yeah, it's true that some people are still awake.
Some people are trying to get in.
No, hopefully not. Thankfully not.
Yeah,
have that arranged.
I will continue with our audience with a quiz. You can also take the quiz later when you have at your own time to see how many things you know.
Let me click the form to see.
Yeah, click the form. Guys, I put the quiz on the chat. You can find it and you can start playing already, and I will start in a bit. I would like to thank so much Grigoris for being here with us today. Thank you, Grigori.
Thank you, Ellen, a lot about the invitation. It was really a pleasant, let's say, hour or something.
Yes, hour or something. Thank you. No, really, I learned so much, and I keep learning every time more and more about the topic that I'm not so familiar with. So
yes,
I'm a bit selfish now. I'm learning more. I hope you enjoyed it, guys. If you have more questions about the topic, email us. We are happy to answer questions afterwards.
For sure. Yeah. Thank you.
Grigori, have a very good night, and we talk soon.
Bye.
Bye-bye. Right. Excellent. So, guys, don't go anywhere, okay? I have the quiz for you. Okay, so let me find it. So this month's quiz was designed by Paul Hombach and myself, and you will find it on the link, and it's about extraterrestrial intelligence. Okay, we're trying to find some intelligence in the universe because lately there is not so much intelligence on the Earth, you know. So we're just trying to find if there is some some out there. Let me share. Let's start together. Okay, let me see if you have put anything on the chat. Thank you, Nadia. Thank you that you enjoyed it. We also enjoyed having you with us. And guys, as I said, feel free to ask more questions. Grigoris can answer anything. Now that he's gone, he can answer anything afterwards. Right. So let me share my screen and we will start the quiz. Is it this one? No, it's this one. Okay. All right. Blah, 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 blah. Share screen. This one. Right. Excellent. So extraterrestrial intelligence. You can put your email here so I can get your results and see if you won or not. So the first one. What is the name of the institute looking for extraterrestrial intelligence? Meta, Tesla, SETI, or Yeti? Which one do you think it is? Tesla, but not so much for outside the Earth intelligence. I mean, he was a very intelligent person. Meta, okay, that's about the metaverse. Maybe it's not that one. Okay. SETI, do you think it's SETI? It sounds a bit also like, to my head, like IKEA, so maybe it's not SETI, or maybe it is, I don't know. Or Yeti, is it Yeti? Let's see. Right. Are there aliens? So here you can write, I don't know, you can write a whole essay. It's up to you. I'm happy to read your answers. Do you think there are aliens? In here, outside, in the solar system, in the universe, anywhere? Happy to hear your thoughts. Right. Excuse me, I'm still getting over COVID and yeah, this fucking shit. Oh, excuse my French. Right, so what was the name of the hypothetical planet within the orbit of Mercury? Okay, so a bit of context. There is a concept that there was a planet between the orbit of Mercury and the Sun. And this planet was called Vulcan, Trantor, Tatooine, or Solaris. Tatooine reminds me of something. But I think this one had two suns. Maybe it's not our solar system. Okay. Trantor, it's a very weird name. Solaris, okay, it could be, but also it reminds me something of, sci-fi movies, so maybe not. Do you think it's Vulcan? Huh? Maybe. Let's see. So, the next one. The most likely place to look for organic life in the solar system, other than on the Earth, is the moon. Is the moon Okay, I didn't read this correctly. Excellent. We are looking for organic life in the solar system other than on Earth. And it's a moon. Is it Europa, Deimos, Triton, or Miranda? You know, Europa is a moon. It's not only, you know, don't confuse it with Europe. It can be a moon also. Where is it? Where is it? Is it on? Okay, you answer on this the chat because my brain freezed. Which planet has a moon called Europa? Good. So, oh, the ominous wow signal, if you know about it, it was the first signal that we thought it was aliens, was received in August 1977 by which radio telescope? Okay. Was it the Big Ear Ohio State University telescope, the Effelsberg, which is outside Bonn in Germany, the Jordell Bank of Manchester University, so this is in the UK, or the Arecibo telescope, which unfortunately was destroyed, I think last year. So which one is it? Is it the Big Ear? Do you think, you know, this is why they named it like that, so it can hear extraterrestrial intelligence? Let's see. Right, the next one. On board the Voyager space probe is the famous golden record, containing samples of world's musical heritage. Okay, we have put a lot of things on top of this golden record, and also some drawings of human beings and other things. So it also has some music, and one of it is Mozart's Queen of the Night, and this is sung by Maria Callas, Edda Moser, oh, I cannot pronounce that, Yacey Norman, Florence Foster Jenkins. Okay, I have to admit, Paul put down that question, and I'm not familiar with it. Let's see if I can help you a bit. Maybe it's one of the names I could pronounce better. Okay, go for the top ones. One of the two. Okay. Where is everybody? Yeah, I'm also asking that. Where is everybody? This is a question about the obvious lack of evidence of extraterrestrial intelligence. Okay, and it was first raised by William Shatner at the after-show party of the first FedCon. You've obviously been there, so you should know. Bill Gates on his first day in his garage startup. Okay. Enrico Fermi talking to Edward Teller in Los Alamos. That's very specific. But it has some, I like this. Enrico Fermi and Edward Teller conversation. Can you imagine? Maybe, eh? Right, let's move on. The real reason we haven't found extraterrestrial intelligence is they live amongst us, maybe. We're alone in the universe. Okay, that's very depressing, huh? But maybe it's true. Advanced civilizations self-destruct. Okay, that is even more depressing because we are an advanced civilization. I don't know what it says to you, but to me, it's a bit depressing. And the last one, we don't have the technology to detect it. Well, maybe that's not true because we have a lot of technology to detect, you know, radio signals that come from the universe. We have a whole program called, you know, the first question. I'm not going to tell you yet. So let's see. This one now. The Arecibo message was sent in 1974 in the direction of the global cluster. Oh, okay, here we have a lot of M13 in Hercules, Omega Centauri, M22 in Sagittarius, or M3 in Venatici. See, Venatici. Right, okay. I don't have it today. TC. Okay. So it's one of the 4. You can gamble here. I would have gambled too. I'm not so familiar with globular clusters. I am, I study galaxies far, 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 far away. Right. In which film featuring aliens? So now we're changing a bit. We're talking about films, sci-fi, aliens. So in which film that is featuring aliens, humans explode, oh my God, explode when in contact with the alien eggs? That's horrible. Who have thought of that? Okay, alien, contact, contamination, Men in Black. If you have seen all of them, congratulations. If you haven't seen any of them, why? Okay, you should definitely see Alien. The first time I watched Alien was on TV and I was a kid. It was bloody scary. But the 80s, we could watch things like that. I think it was the 80s, yep. And then Contact is an amazing film, you should watch it. I went to the VLA once in Socorro, and Jude Foster, what's the name of the protagonist? She has an autograph in the control room. Amazing, amazing. Contamination, I do not remember this film, but this is very relevant. Maybe it's Contamination. And Men in Black, okay, you should have seen that. It's hilarious, okay? Yeah. And if you haven't, you should watch it. Put it on Netflix now. Okay, last one. In which film featuring aliens, the aliens die because they are not immune to Earth's viruses? War of Worlds, The Host, E.T., or Extinction? Okay, that is tricky, You will have to see it. It's also a very popular film, and it has a lot of big names and celebrities. And it's more recent. Okay, I'm helping you. I don't think E.T. exploded. It was a very nice film, so I don't think it's E.T. So, right, excellent. Let's see what you have done. I will stop sharing. I will check my chat. I don't want to reveal everything to you. And let's see. Now we'll reveal. Okay, so some responses are coming in. And I will take you through and we'll go through the answers, but I will not reveal your scores because, I don't want to put you on the spot. So let's do this together. Thanks very much for playing. And I will release the results after we finish. Right. So what is the name of the institute looking for extraterrestrial intelligence? It's SETI. So I hope you got that right? And if you are interested in that, have a look at their website. We have a lot of material also for, known astrophysicists. So have a look at that. It's very nice. Are there aliens? I want to read what you wrote. Okay. No. What are the questions? Are there aliens? 5. Okay, good. Yes. Okay. No. Okay. Yes, with many exclamation marks. Okay. Where is everybody? Yes. Yes, I agree with you. And as I see you and you see me. Okay, that is very poetic. I don't know what this means, but thank you. Right. So the next one. We answered this one. What was the name of the hypothetical planet within the orbit of Mercury? Vulcan. Yes, indeed. It is correct. Thank you for playing. And that's a true name. There is no planet between the sun and, the orbit of Mercury, by the way. We have checked. So, next one. The most likely place to look for organic life in our solar system in the moon is Europa. And you have not answered to me. Whose moon is Europa? I will Google it because I don't like to Okay. Why don't you have it? It's Jupiter. Very nice. Yeah, Jupiter. Thank you very much. Good. Excellent. The next one. So the wow signal. Okay. So it was received by the Big Ear Ohio State University. That's an amazing name. I love it. Inspirational. The next one. On board the Voyager, we have the famous Golden Record, and the Mozart's Queen of the Night was sung by Eda Moser. Okay. Where is everybody? Yes, where is everybody? So this was a question was raised by Enrico Fermi talking to Edward Teller in Los Alamos. I told you, I knew it. So, okay, the real reason why we haven't found extraterrestrial intelligence, and this is the depressing part, okay? Maybe they do live amongst us, you know, who knows? Maybe they have good disguises. Maybe we are the aliens. No, we're not. Maybe we're alone in the universe. You know, no, we're not. I don't think we are. You know, many astrophysicists don't think we are, you know. So the most depressing answer to this question is that advanced civilizations self-destruct because they reach up to a point that, you know, they have nuclear weapons and some idiot pushes the button and kaput. Okay, so that's it. But we do have the technology to detect, and we are trying to detect megastructures around possible, you know, Earth type stars or radio signals that come from the universe that would give us some type of telecommunications in another planet, for example. But we have not detected anything yet successfully. Okay, the Arecibo message was sent in 1974 in the direction of the globular cluster. What is the answer? M13 in Hercules. If you don't know that, it's okay. It doesn't matter. It's a very specific question, but you're doing great. Thank you very much for playing. Okay, the next one. I told you it was contamination. I knew it. In which film featuring aliens, humans explode when in contact with their eggs? Yes, it's contamination, and that's a horrible idea. I don't think I was. Maybe I watched it when I was younger. I don't know, but I definitely don't remember it so good. And the last one, in which film featuring aliens, the aliens die because they are not immune to the Earth viruses. It's War of Worlds. And yes, at the end, after they try to eat everyone and destroy everyone, they start dying. And, you know, this tells us a lot about immunology and, you know, viruses and immune systems. And yeah, so if there are aliens amongst us, surely their immune system has adapted to the Earth conditions, for sure. Great. Thank you very much, guys. I really enjoyed today. Oh, okay. There is a fun fact. Okay, before I say goodbye, thank you very much. Okay, so I think this is Paul. Eda Moser lives in south of Bonn. I did not know that. That's amazing fun fact. And yes, it's Jupiter. Thank you. Sorry, I got a brain freeze at the moment. Hello to Athens from Vienna, Germany. Guys, thank you very much for being with us today. We really had a good time. I really enjoyed your company and Grigoris' company. I hope you enjoyed the true or false, the discussion, and the quiz. If you have any special requests about a quiz topic, for example, feel free to share it with me. The next Astronomy on Tap is in May, in a month, right? The second Tuesday of May. And this should be, blah, blah, is the 10th of May at 7 p.m. Central European summertime. So we changed the clocks. Thank you very much. If you want to rewatch this, it's going to be available on YouTube. Don't forget to like, subscribe, and follow on all social media, Facebook, Instagram, Twitter, TikTok. Yes, TikTok. What else do we have? Twitter. I said Twitter. Yeah. That's it. Have a very good night.